we now introduce some limits that are of more typical nature that are normally found in a calculus course. So we'll do these first two examples, and by the way, examples in the textbook can be found in section 3.1. So here we're faced with this first limit problem, and it's a limit of a quotient. Every time you're faced with finding the limit of a quotient, the first thing you should always check is the limit of the denominator. For any quotient, you always start there first. Well, the denominator, if you look at the denominator is a linear function. And we know that we can find the limit of a linear function by direct substitution. So when I substitute 2 in for x, I get 2 minus 2. That gives me a limit of 0. Since the limit of the denominator is 0, it's possible that this limit doesn't exist. So my next check is to take the limit of the numerator. Looking at the numerator is a polynomial function. Again, we can find this limit by direct substitution. Doing a direct substitution, and we get that the limit of the numerator is 0. So by property 6c, our conclusion is that this limit is indeterminate. All that tells us is that we really don't have a clue yet as to whether or not the limit exists or does not exist. So I'm going to put a little box around here. This is always the first computation you do whenever you're faced with finding the limit of a quotient function. So now, where do we go from here? Well, what we want to do now is we want to replace the entire quotient function with some other function whose limit is determinate. So looking at the numerator, realizing the numerator is a polynomial, and what I found that I really have found that 2 is a 0 of that polynomial, which means that it is factorable. So I'll proceed by factoring the numerator. The numerator factors into x minus 2 times x plus 2. It's a difference of 2 squares. The denominator is x minus 2. Notice that I write LIM. This is only true in limit. These two expressions are equal. I put an equal sign because it's only true for in the limiting sense, not as expressions by themselves. So the next thing I noticed, I can cancel out this linear factor of x minus 2. And the limit problem now says find the limit of x plus 2 as x approaches 2. This function that we have right here, as I was saying in class, you don't really pull a replacement function straight out of the air. What you normally do, you do some algebraic manipulations, and then it'll fall right out what the replacement function is going to be. In this case, the replacement function is linear, and we know that we can find the limit of a linear function by direct substitution. So I do a direct substitution, and my limiting value turns out to be 4. Now, I want you to notice the layout of this example here. What I'm talking about, notice how the string of LIMs that are placed into the problem, when I'm ready to evaluate the replacement function, there's no LIM because the 2 plus 2 represents the actual limiting value of this linear function. So at that point, I don't put the LIM in front of the 2 plus 2. So the limit of this quotient function turns out to be 4. And by the way, this was nothing more. This was the introductory example from the 5-page limit handout. Well, let's try it again. Here's another example. Got another quotient. The limit as x approaches 4 of the quantity x squared plus x minus 4 divided by x squared minus 4. Again, now notice that both of these examples, example 1 and example 2, they are really rational functions. But the problem is that I'm approaching a number that's not in the domain of these rational functions, so I cannot find the limit by using the limit rule for rational functions. That is, doing a direct substitution. Again, I'm going to treat this as a quotient function. So I proceed, change colors, by looking at the limit of the denominator. Always denominator first. Now the denominator is a polynomial. Again, find the limit of that polynomial function by direct substitution, and I get 0 for the limit of the denominator. So then I proceed to find the limit of the numerator. And by the way, if it turns out that the limit of the numerator doesn't turn out to be 0, then by property 6b, the limit of the original quotient does not exist. But as you can verify this when I do a direct substitution, the numerator being a polynomial as well, I get a limit of 0. You should always check to make sure that the limit of the numerator and the limit of the denominator are both 0. If you don't do the check, there is an example coming up where you don't really have to find a replacement function if the limit of the numerator and the limit of the denominator are both not equal to 0. If one of them doesn't equal 0, usually if the limit of the numerator doesn't equal 0, then the limit's not going to exist. If the limit of the denominator doesn't equal 0, then you can use property 6a, which says you can just take the limit of the quotient is just the quotient of the limits. Okay, so let's proceed here. Now that we know that it's indeterminate, now we got to find our replacement function. So I'll take the limit of this expression by factoring. I notice the denominator is factorable. It's a difference of two squares, x minus 4, x plus 4. The numerator is a trinomial. Well, let's see how long it's going to take for it to... Okay, here we go. Oh, he wants me to save this. That's fine. The numerator can be factored into x plus 5 and x minus 4. Again, cancel out this common factor. And that leaves me with the expression x plus 5 over x plus 4. So my replacement function, this is it right here, is classified as a rational function. So what I notice now, I'm taking the limit as x approaches 4. Notice that 4 is in the domain of that rational function. So I can find this limit by doing a direct substitution. Oh, I'm sorry. I don't need to write the LIM anymore. I'm ready to evaluate this limit. So by doing a direct substitution, I get 4 plus 5 over 4 plus 4, which gives me a total of 9/8 for the limiting value. So we'll put a little note here. This is a rational function with 4 in the domain. I don't like the way that looks there. So as you can see in both of these examples, the replacement function will come out as we algebraically manipulate the original function. Okay, there's two examples there to get you going on these indeterminate limits.